I'm here. I'm here. Sorry, I didn't know we had started already. I'm sorry for being late. You'll not believe the traffic. But welcome to week 4 of Stats and Research 2. This week we're going to focus on correlations, simple correlations, not to be confused with some of the hypothesis testing that we're going to do later in the semester. One of which is a correlation, where we just look at two continuous variables. But this week we're just going to introduce that idea of correlation, of two variables being related to each other, whether they're independent and dependent variables or not, but just that there's a relationship between two variables. So let's get started. Simple correlations. So when we deal with correlations, when we talk about correlation, we're going to talk about a correlation coefficient, which we represent by R. And then if we write out R, X, Y, that just means correlation between X and Y, two variables. A little confusing, I know, but the number R is going to be a value that's between -1 and 1. And I'll explain all this in a moment, but it's another way of looking at it is 0 to 1 being both negative or positive. Negative value is going to represent a negative or indirect relationship, correlation. Positive number is going to be a positive or direct. The closer the value is to 1, the stronger the relationship between those two variables. So we're measuring how the value of one variable changes in relation to changes of the other variable. We're dealing with bivariate here, meaning two variables, bivariate correlations. So a 0 is going to represent no relationship whatsoever, and then the closer we get to -1 represents a stronger negative relationship, and then the closer we get to +1 represents a strong positive relationship. Makes sense so far? I think so. I hope so. There's a little bit different terminology that can be used in terms of directions of correlation here. So positive correlation can also be referred to as direct correlation, and negative as indirect. So we call it direct because the variables change in the same direction. The direct correlation, when one variable increases, the other variable increases as well. And we're going to represent this with an R of 0 through 1. Like I said, it's a positive correlation, a direct correlation. So we represent that with an R, a correlation coefficient of a positive number. If we're dealing with a negative correlation or an indirect correlation, meaning that the variables go in opposite directions. So when the first variable increases, the other variable decreases. And I'll show everybody some visuals in a moment that should help this out a lot. But the R, the correlation coefficient in this situation, would be represented as -1 through 0 or 0 through -1. So a negative valued R is going to represent a negative correlation, meaning that as one variable goes up, the other variable goes down. As I said, there are different strengths. 0 is going to be no correlation whatsoever, and then the closer we get to 1, whether positive or negative, is going to represent the strength of the relationship. So we can have a strong positive relationship. This is positive. As you can see, if we look at the x-axis and the y-axis, the x-axis, as those values go up, they go up with y as well. If we were to look at these values, all these dots represent values. So we can see that with an x value of 2, we also have a y value of 2. With an x value of 5, we also have a y value of 5. So we're not sure what those represent. They could just be different counts and things like that. This is actually a perfect correlation, a direct, perfect direct positive correlation, meaning with every increase of one variable, there's an equal increase of the other variable. So these don't happen very much naturally speaking. They're not found in nature very much. They're not really found in criminal justice research very often because it's not likely that you are going to have two variables that are connected so strongly that are just randomly existing. Some examples that you could look at, which again are not really natural, based on maybe policy. If a police department has a policy of adding a new officer each year, then you could see that increase, but that's not naturally occurring, and there's definitely a relationship between those two because we know in context there's a policy relationship there. Also, there may be some other policy guidelines in place through IDOC or something like that, where given a certain number of inmates, you should also have a certain number of correctional officers. So if we looked at those values, we could see a standard increase with correctional officers based on increases in inmates. But again, those aren't really naturally occurring. Those are just based on policy that's in place. So a strong positive relationship, not a perfect relationship. Sorry about that, everyone. Let's take a look at this one. The dotted line is added in. Those aren't points. You can see the gray points are the actual values that are being represented here. And I made it a dotted dashed line as opposed to a solid line because it's not a perfect relationship, not a perfect correlation, but based on where those values are and the X and the Y values, we can see that there's a certain relationship between those. And I'm not sure what the correlation coefficient is. I just guessed, I just hypothetically said it was 0.48. So it's positive, it's not a negative value because we see the arrow going up in this situation. As X is increasing, Y is increasing as well. It just based on those values I saw, not an amazing correlation in terms of strength, but generally 0.5 and above are what we consider strong relationships. Everything else 0 to 5, there's kind of varying degrees of like weak, moderate, moderate, weak, moderate, strong, strong. But generally speaking, about 0.5 and up, some people say 0.7 and up is considered a strong relationship. So this is somewhat strong, not amazingly strong. Some examples where we might see a strong positive relationship in the criminal justice world. If you look at city population and homicides, most often you're going to get a pretty direct relationship between direct correlation between population and homicides as population goes up, and that would be the X value, because number of homicides isn't going to determine the city's population, right? I guess it would affect it to a certain degree by decreasing it, but as the city population increases, we look to see where homicides go. And if homicides increase, which usually happens, the bigger a city, the more homicides there are, then that would be considered a positive relationship. If you look at individuals and sentencing data, perhaps, and you look at prior arrests, so X value of prior arrests, and then current sentence length. So the idea here is that when we talk about sentencing, if that's the Y value, the prior arrests come into consideration when somebody gets a sentence. So as prior arrests increase, it's very likely that the current sentence length is also going to increase. So that would represent a positive relationship as well. And then if you look at police officers' years of service and numbers of arrests overall, compounding number of arrests, then that should be a positive relationship. That should just continue to go up unless there's some sort of plateau with administrative duty or something along those lines. And then a negative relationship. We're always going to have the relationship be with positive values, so to speak, because we won't really have an X value going negative. So as the X value increases, we're still looking to see what happens with the Y value. And if we have a situation where as the X variable increases, the Y variable decreases, then we would have something similar to what you see here. Again, the dashed line is something I added, kind of a line of best fit to fall in with those values that we see kind of going down basically. As x increases, we see a decrease in y. Very common example of these or something like this would be what we've been experiencing overall for the past 30 years or so is a crime rate decrease. Right, crimes in year. The x value in that case would be time, or specifically years probably, and number of violent crimes, number of homicides, whatever. In general, we're trending downward, and we have been for a long time. So you would see a trajectory like that. Also, maybe something like income and criminal record. I guess if you were to look at number of arrests as an x value, maybe then income as a y value. So these are, it's we see these a lot when we take time into consideration as a variable, so usually an x variable. And so we can see a relationship, a negative relationship at that point. The r value, negative 0.65, is just kind of hypothetical. But again, this looks maybe a little bit stronger than the previous correlation. It's negative, so r is going to be a negative value. And here's what I was talking about earlier. This is what your book says. Again, there are some varying opinions on that. I've tended to hear and go along with the idea that 0.7 and higher is strong or very strong, maybe. And something to consider, what we're talking about here is correlations, right? We're not talking about causation. And that seems technical, but there's a big difference between the two. Oftentimes people will look at two variables, and if there's a relationship between two, they will say that one is causing something else to happen. Okay? Just from looking at this, we can't necessarily indicate that. We can just say that these two variables are correlated. Sometimes there may be some omitted variables that are also having an influence on this outcome variable, this dependent variable. So a couple things need to be in place. So do not confuse correlation with causation. Correlation does not mean causation all the time. And that's a mistake we don't want to make, because then we can attribute the cause of something to some other variable that may be interacting with it in some way. And that can especially be problematic if we're looking at something like crime. And if we're looking at crime as an outcome variable, and we see a relationship and a correlation with crime and another variable, say that number of whatever the case is, population increases and then crime increases as well, and we're not taking into consideration other things, then we may erroneously make this causation determination and say that this first variable is definitely causing crime, when we're not sure if it necessarily is, because we have to keep a couple things in mind. Again, and I kind of alluded to this while we were going through those examples, but there needs to be an order in place to at least even consider something causing something else, because we know that if we're going to say that an independent variable is causing something with a dependent variable, we need to know that the independent variable is coming before the dependent variable. During our discussion before, I gave an example of how demographics are almost always going to be independent variables as opposed to dependent variables. Same with time, for instance, because there isn't going to be any type of variable that's going to determine demographics or determine time. Those are pre-existing, so those are going to precede any type of dependent variable that you would look at. Empirical relationship, we have to see this relationship. This isn't obviously just a theoretical thing, but we have to have this observed relationship that we see actually happening when looking at these different values. in non-spuriousness. This is the idea that the relationship between the two variables, the independent and dependent, must be because of those two variables, and there must not be a third or possibly several more variables that have been omitted from that analysis. And what exactly does that mean? If we have a situation here, we're looking at x and y as these variables that we've been discussing, and we see a relationship between those two. There may be a third variable in this situation that's affecting x and it's affecting y. So looking at x and y, we see that there's a relationship between the two, and we want to say causation. We want to say x causes y, but at the same time, z might be affecting x and z might be affecting y as well. So we can't specifically say that it's x that's completely causing y because z is thrown in the mix as well. We call that the omitted variable bias. We call it spuriousness when we have that third variable, and the omitted variable bias is when we don't take into consideration that spuriousness and the idea that there could be a third variable incorporated. As we're just doing these exercises looking at simple correlations, that's not that big of an issue. But if we were to make inferences from this and try to establish causation, we would then need to make sure that there's not some third variable included. So it can lead us to incorrect conclusions. And it can be a very significant problem in criminology and criminal justice research because, like I said, we have dependent variables like crime, victimization, other things that we're trying to figure out why they exist. We're trying to figure out why people commit crime. We're trying to figure out what happens when we put into place certain correctional practices. So if we're incorrectly attributing causation to a situation where things are just correlated, then that can be a problem with policy that we're making. Now let's look at an example. Excuse me. Let's look at an example to try to bring this into context. Suppose a researcher found a statistical relationship between ice cream sales, X variable, and crime, Y variable, dependent variable. During months when a lot of ice cream is purchased, crime rates are higher. The research concludes that ice cream causes crime, causation. What has the researcher done wrong? So, the answer is probably a lot. The answer is obviously connected to what we've just been talking about, right? He attributed causation where there's really just correlation. So he's saying that there's a strong relationship, a strong positive relationship between X, which is ice cream consumption, and Y, which would be crime in this situation. The more ice cream that's consumed as X increases, as the number of people consuming ice cream increases, the number of sales, whatever it is, increases, then the number of crimes increases as well. Makes sense. But is it possible that there's this spurious omitted variable that we need to take into consideration? There could be something that is affecting ice cream sales and affecting crime increasing at the same time. However, it's affecting them both enough to the point where we can't say that ice cream is really the reason that crime is increasing. It sounds silly to start with, so we think those two probably aren't causally connected with causality, but there's maybe some other variable that's actually affecting them both that can explain why they're both going up. Because in a positive relationship that we're seeing here, both are increasing. So is there possibly something that's increasing ice cream sales as well as increasing crime? So if we think about that for a minute, there could be a couple different things. It's really the same type of idea that's influencing things, but outside temperature could easily be something, especially if we're in an area like the Midwest, Chicago, where we have varying seasons and big shifts in temperature. But If the temperatures are warmer, people tend to consume ice cream more. Places like Dairy Queen, for instance, usually close down during certain parts of the year, during seasons of the year. Crime in general also goes up in the summer, and that's pretty much across the board. Has been a pretty consistent trend, and that's for a couple different reasons. People are, school. A lot of people who commit crime are in a school age range, whether it's high school into college, and that commitment is no longer present during the summer. People don't have school to go to, so they have more time on their hands. It's also warmer out, and in certain situations, depending on how warm it is, you're going to have people outside a lot more. So that sets up a scenario where there might be issues. And just in general, people commit crime. People are out more, especially when you compare it to the cold seasons. So we see something like temperature and a season more really, and time, months of the year, whatever, that's going to affect increased ice cream sales because of not just certain places not being open during the winter, but of course people like to be outside and eating ice cream more in the summer. So that's being affected by the time of the year, as well as crime for a number of different reasons. So if you look at those two variables, but you omit this other variable of temperature, time of the year, summer, you can just call it summer if you want, then you're ignoring this factor that is going to affect both of these variables. So again, that's having nothing to do with causality. Ice cream, despite even there could be a very, very strong direct correlation, strong positive relationship, but that doesn't necessarily mean causation occurs. There are these other factors that we need to take into consideration. The book does say association versus causality a lot. I'll usually say correlation versus causation. So again, just kind of different verbiage. So these correlation coefficients, it's that R value that we'll see in the text and whatnot, shows how things are related, positive, negative, the strength in which things are related. It's used as descriptive, but also can be somewhat inferential to a certain degree. And it just indicates that relationship and correlation, it doesn't really do anything about causality. It doesn't discuss causality, even if it's like that first example I gave where it's a 1. It's a perfect relationship, perfect correlation. That still isn't telling us that it's causation, just correlation. We use other tests later on, and some of them we won't even get to, but we use those other tests later on to determine causality. So it gives information about the relationship, the correlation coefficient itself. I just mentioned a couple of these things already, but gives us an idea of how these other variables are changing when one variable changes to start with. So that is simple correlations. Again, we're going to talk about correlations in terms of hypothesis testing in a number of weeks from now. But the thing you want to remember from this week is you want to remember the differences in positive and negative correlation, direct, indirect correlation, and then correlation does not mean causation. That's a big one. Take into consideration, especially when we're getting to our research projects and whatnot, that just having two variables together and having a relationship between the two of them doesn't necessarily mean one is causing the other. There's a number of different variables that could be included that would have a spurious effect on influencing that outcome variable. So I will see everyone next week, and that's it for this video. Take care. Here we go. Take care.